start recording. Now you can put your names because before recording they will not be recorded in chat too. And now let me start screen demonstration. Let it be total screen demonstration. So you'll see everything I'm doing on the computer. I have opened again the lecture 6 file. You can find this file in the folder with my PDF presentations for lectures. And we stopped last week, 2 weeks ago on last lecture, we stopped at electromagnetic radiation. We have discussed the various wavelengths in electromagnetic spectrum. And now let us discuss some things related to so-called geometrical optics. It is the laws of refraction and reflection. So here is the law of refraction, which is called also Snell's law. Wait, I'd like to show you the top of my page, but now it is seen. So if someone writes on chat, the extra screen appears and you cannot see the top. Anyway, it is Snell's law, exercise number 9. So the refractive index shows the ratio of speed of light inside the substance related to the speed of light in vacuum. The speed of light in vacuum is maximal speed which is possible in our universe, and this speed is not infinite. It could be infinite, but it was found from many various experiments that the maximal possible speed of transmission signal is restricted, and it is equal to the speed of light, and it is about 300,000 kilometers per second. So in various substances this speed is smaller, and the ratio of the speed in vacuum to the speed in the substance is called refractive index. And if the light goes from one substance with refractive index N1 to the substance with refractive index N2, then for the angles of refraction we have this relation which is called Snell's law of refraction. And from this Snell's law we can obtain the result that we can use lenses for control the distribution of the propagation of light beam and for forming of images. Actually, our eye is a sort of optical system which forms in real image. We'll discuss it a bit later. But first, let us discuss simple lenses. They can have different shape: biconcave, planar, convex, positive meniscus, negative meniscus, and you see planar concave, biconcave, biconvex, first one. So these lenses can be used for forming images. Let us see how it can be done. So here are the way of light beams in a lens. If we have a biconvex lens, it is called positive. Actually, every lens which makes the parallel light to converge in some point are called positive. And if the light beams which were parallel goes divergent, then the lens is called negative. If we analyze Snell's law for the light beam on spherical surfaces, and if we use small angle approximation, we can get this equation for focal length. Focal point is a point where the light beams crosses after passing through the lens. In case of positive lens, this focal point correspond to real crossing of light beams, and in this point the parallel beams create a strong intensity. Wait a second, let me in case of negative lens, these lights are crossed in a point which has no actual intensive light. So this sort of crossing is called image let's say point, and I have told already that using Snell's law we can find the length from the lens and focal point. So this distance, which is called focal length, can be found from Snell's law, and it is given by this equation, which is called lensmaker's equation. Here are radius of curvature of lenses, of surfaces of lens, and n is refractive index. So the radius of curvature present here with sign, and it is positive if the lens surface is if the center of curvature is closer to the light source, and negative in opposite case. So for biconvex lens, these two radius of curvature will be with the will present in this equation with the same sign. And the value of 1 divided by f is called optical power of lens, and it is measured in diopters. So it is equal, 1 diopter equal inverse meters, and the larger optical power, the shorter focal distance, and the stronger refraction in lens. So the lens with a higher optical power can produce strong change in, for example, vision correction, stronger change. Well, next is the thin lens formula, which can be obtained by the considering of light propagation in a thin lens. The lens is called thin if we can neglect its width compared to its size and its focal distance. So if focal distance is much larger than width of lens in its thickest part, then we can call this lens a thin one. And for this lens, the following equation can be written, where S1 is distance from object to lens, S2 is distance from image to lens, and F is focal distance. Let us see a short video now. So let me start. For example, we can use this. I have taken the link from the file, links for video for lecture 6, and I hope you will be able to hear the sound too.
Image formed by convex lens. To find the position of image, draw three rays starting from object. Draw an incident ray parallel to optical axis. After refraction, it passes through second principal focus f2 of a convex lens. Draw an incident ray passing through optical center O. After refraction, it emerges without any deviation. Draw an incident ray passing through the first principal focus f1. After refraction, it is refracted in a direction parallel to optical axis. Image is formed at a point where these three rays intersect. When object is placed beyond 2f1, image is formed between f2 and 2f2. Image is diminished, real, and inverted. When object is placed at 2f1, image is formed at 2f2. Images of same size, real, and inverted. When object is placed between f1 and 2f1, image is formed beyond 2f2. Image is enlarged, real, and inverted. When object is placed at f1, image is formed at infinity. Image is enlarged, real, and inverted. When object is placed between f1 and O, image is formed on the same side as that of the object. Image is enlarged, virtual, and erect.
Well, now let us go back to our lecture. So you have seen that using a single lens, we can get different type of images. We can get real and virtual images. We can get enlarged and diminished images. And with the negative lens, we can get only virtual images. There is no way to get real one. Anyway, negative lenses can be used for some reason, and they can be a part of a complicated optical system. So they can be used for vision correction. So they are also widely used. And if we discuss linear magnification, you see it is not a characteristic of lens It is a characteristic of distances from object to lens and from lens to image. So it can be different, and there is no such a characteristics as magnification for a single lens. Another situation is in case of optical system. I will discuss telescope and microscope briefly there. The magnification is a characteristic of system itself. So let us see how a telescope, a refractive telescope, can be constructed. In this case, we have an objective lens with a long focal distance. It forms an image of object which is located very far away, we can say in infinity. Then the image is formed in focal plane, and this image is then seen using the objective lens with eye. So it forms a virtual, the objective lens in this case forms a virtual image. And this virtual image appears here, it is enlarged compared to the object. So this optical scheme allows us to get it is virtual image. It also allows us to get a real image if we want to make a photograph of the stars, for example. But if we want to look with eye, we need to have a virtual image at the distance of best vision. It is about 25 centimeters. And the magnification in this scheme is equal to the ratio of focal distances for objective lens and for the eyepiece lens. So the larger this ratio, the longer tube we need to use, because if we want to get higher magnification, the focal distance of objective lens should be large. That's why we need a long tube. So the similar principle is used in a microscope. The only difference is that the objective lens here is a short focal length, so it has shorter focal distance than eyepiece lens. And again, if we use an eyepiece lens, and the image is virtual and it is seen with eye, and it is seen as an image formed at distance of 25 centimeters from our eye. So here is the simplest scheme of a microscope. Of course, real microscope have a few lenses in objective, and there are some. It is not a simple problem to create an optical system for a microscope. And basic principles can be understood from this simplified scheme. Now let us discuss the optical system of our eye. And again, I would like to start with a video because most of things can be said there. And wait a second, I will just use the second link from here, which is a short video about human eye, about 5 minutes.
The human eye. We know that a lens is an optical device that transmits and refracts light. Our eyes too have lenses that enable us to see objects around us. Let us see how the eye is put together and how it works. At the very front of the eye is a transparent structure called the cornea that helps to focus incoming light. Behind the cornea is the iris. The iris has a circular opening called the pupil. The pupil expands or contracts depending on the amount of light entering the eye. Situated behind the pupil is a colorless, transparent crystalline convex lens surrounded by the ciliary muscles. The muscles hold the lens in place and help to change the focal length by adjusting the curvature of the lens. To view a distant object, the muscles relax, the lens becomes thin, and its focal length increases. To view a nearby object, the muscles contract, the lens becomes thick, and its focal length decreases. This ability to adjust its focal length is called the power of accommodation of the eye. The image formed by the lens is a real inverted image of the object that then strikes the retina. The light-sensitive cells in the retina convert the light into electric signals that are relayed to the brain. The brain converts these electrical signals into the images that we see. The minimum distance at which the eye can see objects clearly is called the near point or least distance of distinct vision. In a normal eye, it is 25 centimeters. The farthest distance up to which the eye can see objects clearly is called the far point of the eye. In a normal eye, it is between 25 centimeters and infinity. The eyes can gradually lose their power of accommodation, resulting in blurred vision due to refractive defects. There are 4 common refractive defects of vision that we shall look at and see how they can be corrected. The first defect we look at is hypermetropia, also known as far or long-sightedness, in which nearby objects cannot be seen clearly as the image is formed behind the retina. This is due to the increase in focal length of the lens and decrease in the length of the eyeball. This defect can be corrected using convex lens of suitable focal length. The next defect is myopia or short-sightedness, in which distinct objects cannot be seen clearly as the image is formed in front of the retina. This defect may be due to the increase in curvature of the lens or due to the increase in length of the eyeball. This defect can be corrected using concave lens of suitable focal length. The third defect we look at is presbyopia seen in elderly people. Here, nearby objects cannot be seen clearly due to the increase in the distance of the nearest point. This may be due to the weakening of the ciliary muscles or due to the decreased flexibility of the lens. This can be corrected using a convex lens of suitable focal length. At times, both nearby and distant objects cannot be seen clearly, and this can be corrected using bifocal lens. The upper part is concave.
Let me stop it for the moment. Here is a mistake in the picture in the video, and she said it correctly, but the image shown on the picture is not right. Let us listen again about biconvex lens, bifocal lens.
Lens. The upper part is concave, correcting distant vision, and the lower part is convex, correcting near vision.
So it is said that upper part and lower part should have different curvature, but on the picture you can see outer part and inside part. It is not right. The right is that upper part of the glass and the top of the glass and the bottom of the glass has different surface, different radius of curvature. That's why it is not because of different radius of curvature for inside and outside. It is because of different radiuses for one part and another part. There are two lenses actually if we are discussing bifocal lens.
Astigmatism is another common problem seen when the image may be clearly focused on the retina in the horizontal plane but not in the vertical plane. This defect may be due to an irregular curvature of the cornea or lens. This can be corrected using glasses with cylindrical lens. Things to remember. The ability of the lens of the eye to see near and distant objects by adjusting its focal length is called the power of accommodation of the eye. In hypermetropia, nearby objects cannot be seen clearly. This can be corrected by using a convex lens of suitable focal length. In myopia, far-off objects cannot be seen clearly. This can be corrected by using concave lens. In presbyopia, both nearby and distant objects cannot be seen clearly. This can be corrected by using bifocal lens.
Let's stop it and let me show you bifocal lens, for example. You can see that glasses with bifocal lens look like that. It is actually contain two lenses, one the big one and some smaller attached to it, which allows the vision of nearby objects usually. And there are modern type of bifocal lenses, for example, represented here. So it is the old style when lens for nearby vision is attached to the general glass, and the modern one is very focal when the lens is negative on the top and positive on the bottom, and it changes continuously from negative to positive. Well, let us go further and let us discuss the forming of color image in our eye. So we have discussed optical system of eye. You have seen it in the video, but one important property of our eye is the ability to see different colors. And how it works, how can we do this? It is based on appearance of three types of cone cells. There are two basic groups of cells in our retina. First group is called rod cells. They are responsible for black and white vision of highly resolution and highly sensitivity. So rods are much more sensitive than cones, and they allow one to see the details, smaller details than rods, but than cones. I'm sorry, but rods cannot see the difference between colors, and in case of low intensity of light, in case of night vision, only rods are able to absorb light, and cones require much high intensity, That's why in case of low intensity of light, we cannot see colors, and everything looks like gray, like colorless in night vision in case of low light intensity. And once again, how can we differ different colors? It is based on appearance of three different cone cells. Each cone cell is responsible for each wavelength. And here is a schematic representation of sensitivity for different type of cone cells. These two pictures represent the same quantity, but in different normalization, in different height of curves. In this case, all the curves are normalized to the same maximum value, so it can be considered as percentage of ability of seeing for different type of cone cells. So this beta is for blue cone cells, gamma is for green, and rho is for red. And you see that actually the range of sensitivities for red cone cells and green cone cells are overlapping, and this is a wide range of overlapping, and there is a range where all the sensitivity of all cone cells overlaps. And if we have a mix of cells from different cone cells, we feel we interpret it as a, for example, or a yellow light, or blue light, light blue light, green blue, or green yellow, orange, and so on. So all the intermediate colors are obtained as a mix of signals from different cone cells. And the second picture represents the same dependencies, but with different normalization factor. In this case, absolute sensitivity is represented, and we can see that green cone cells are most sensitive. That's why our vision, so our eye is most sensitive for green light, and blue light is less sensitive. So if we have the same intensity of red, green, or blue light, then green would look like the most intensive, like most bright. Next thing is that since we have only three types of cone cells, or every optical sensation can be obtained by stimulation of these three cone cells, and that's why we can see a yellow light, and we can represent, we can interpret the light sensation as yellow if we have a mix of red and green light. So this phenomenon is widely used in computer displays. And for example, right now you are looking at a screen, and actually there are no light with the wavelength of 580 nanometers, which is interpreted as yellow. So actually there is some light with wavelengths of 560 nanometers, green, and some light with wavelengths about 620 nanometers, which is red. So mix of this red and green creates a sensation similar to yellow. So we interpret this part of a picture as yellow light, but actually there are no yellow light here. There is a mix of green and red. And white light is a mix of the whole spectrum. It's a special mix because if there is some extra red or extra green light, we will see it as light green or light red, something like pink or light blue. But if we mix these lights in a special proportion, then it will be sensed with our eye as a white light. So one way is to combine all the colors of rainbow into one point, and it will be seen as white points. Then another way is to get some mix of red, green, and blue, which is interpreted as a white light with our eye. So this is the basic principles of color vision. So we have three types of cone cells, and each type is responsible for vision of its own spectral range. And here is again the picture of different unperfectness of optical system of eye, hyperopia, myopia, and that's all with the previous lectures, lecture number 6. Now let me open the lecture number 7. Oops. So we will continue our study of electromagnetic radiation in this lecture, and let us discuss such a phenomenon which is called total internal reflection. This phenomenon appears when the light goes from optically denser substance into less dense substance. In this case, the angle of refraction increases, and the angle of refraction is measured between the light beam and vertical, perpendicular to the surface line, the line which is perpendicular to the surface. And you see initially for the first light beam, for example, the initial angle is 20 degrees, outside it is 27. If it is 30, it is 42. If it is critical, which is shown here as 42.8, it depends on different matter. Here the picture is for water with the refractive index 1.33, and the critical angle for water is 48.8 degrees. If the angle becomes critical, then the outside refracted angle is 90 degrees. So the light goes parallel to the surface. And if the angle is larger than critical, then light doesn't go outside at all. So it comes inside. And this is called total internal reflection. It allows to save the light energy, and it is used in optical fibers. So if we made a fiber of something, for example, if we made a tube with glass cells and try to transmit light inside this tube, then part of light energy will be lost at every reflection, because from air light always can penetrate to the glass at any angle of incidence. But if we made the tube of glass, then outside surface, on the outside surface, we can see the total internal reflection, and all the energy is reflected back into the glass tube, and this lead to transmission of light without loss of its intensity. And it is widely used in optical fiber. Optical fiber is used very widely for communication systems. We have now our conversation on internet, and somewhere signal goes through the optical fiber. Only the last mile is now with conventional metal wires. All the rest, for longer distances, the signal is transmitted by optical fibers. And where it is used in medicine? In medicine, it is used for source of light in stomach investigation, where the smoke camera is inserted inside human's stomach, and the source of light can be used. It can use the optical fiber for transmit light inside. It is a very thin and very bright source of light. The obtaining signal from this camera by optical fiber is not very useful, because the resolution is not very high. So the electronic camera is better than a set of optical fibers. But as a source of light, optical fiber is a very good instrument. Well, next phenomenon related to the light is its polarization. So the previous one was total internal reflection. Now let us discuss polarization. We have said that light wave is an wait a second. It is transverse wave. So the direction of oscillation of electric strength vector is perpendicular to the direction of light propagation, and it means we can obtain polarization. We can make this electric vector to oscillate inside one plane only. There are some substances which allows us to obtain polarized light. These substances are made of molecules with which are strongly inhomogeneous. They are not inhomogeneous. They are long on one side and have a small size in another direction. That's why such molecules strongly absorb light polarized in one direction and does not absorb light which is polarized in opposite direction. And if we have a substance made of this molecules orientated parallel to one axis, then this substance would work as a Polaroid. It will polarize light. And again, this is widely used in many devices. Again, the display you are using to watch this lecture uses light polarization to control the intensity of signal. To form the image on the display, we need to change the intensity of light from different points, and it can be controlled by changing the angle of polarization. So if we have two polarizing objects and one of them makes the light polarized, the second one is called analyzer, and if its axis of polarization is perpendicular to the initial axis of polarization, then there are no light passing through the second one. If it is located parallel, then the whole light passes through the second polarization without change of intensity. And we can put some objects which rotates the angle of polarization. There are some substances which can do this, and in case of displays, this substance is used. Its angle of rotation depends on electric voltage applied to this substance. This substance is called liquid crystals. If we put liquid crystal between two polarizers, then applying voltage to these liquid crystals, we can rotate the axis of polarization. And that is how we can control the intensity of outgoing light. The next application of this phenomenon is a medical investigation, because there are some substances which is important from medical point of view, which also rotates the axis of polarization. One of these substances is sugar. The concentration of sugar can be measured using the device which is called Polarimetry, which contains a long tube filled with liquid, and the edges of the tube are covered with glass, so they're transparent. And when light goes through this long tube, its polarization axis is rotated. And the angle of rotation depends on length of the tube. That's why we need long tube. It depends also on the concentration of sugar. So by measuring the angle of rotation, we can measure the concentration of sugar in the examined liquid. So sugar is not the only substance which rotates the angle of polarization, but it is one of the simplest example. And you see here the old style device, one of the first example of these devices, and the vessel for the device can be seen in this part of figure. And this is a modern one. The tube is shorter because the angle is measured not by human eye, it is measured by automatic system, and it allows much more precise measurement. And so we need a smaller amount of liquid. We can do it automatically, but the principle is the same. So the physical principle is the rotation of axis of polarization, which allows one to measure concentrations. Now, next phenomenon we will discuss briefly is interference. Interference can be described as follows. If there are a superposition of waves, then the intensity of resultant wave differs from the sum of intensities, because in case of coherent waves, the not intensity but amplitudes are added, and actually not even amplitudes, the signals itself are added. In case of electromagnetic radiation, it is vectors of electric field and magnetic field which are added, and the intensity is proportional to the square of this vector. That's why when we have a sum of two vectors, and for example, if the amplitudes are equal, and we have sum of electric vectors, we will have twice electric in electric intensity, but only the intensity will increase 4 times. So let us see these equations for interference. These are equations describing interference. So electric field vector is a sum of two electric fields produced by two waves, and that gives us the following equation for intensity. So you can see that it is not just I1 plus I2, it contains interference term, and this term depends on phase difference between two lights. If this phase difference equals 0, then this term is positive, and it gives rise of intensity. In case of equal intensities, then intensity become equal to 4 I1, not 2, as it would be without interference, but 4 I1. If if the phase equals pi, phase difference, it means the waves come into the point in opposite phase, then cosine phi equals -1 and intensity equals 0. It is called destructive interference. And the interference lead to redistribution of wave energy. Some points get higher energy, some points get lower energy. And this is wave phenomena which appears if we deal with the sizes which are of the same order as wavelengths. For example, for light, this is very small sizes. Light has wavelengths of about half a micrometer. So if the object has the size of about 1 micrometer, or a source of light has this size, and we have coherent light source, then we can see interference phenomena. Actually, using some optical scheme, we can see interference for big objects. There are some experiments, for example, double slit experiment, which can be done on microscopic slits with microscopic distance for a few millimeters between them, but it requires some lenses to see the interference picture. Now let us see what we can get from interference, how we can apply it. One application is interferometry. It is a method of measurement which is based on interference, and one of the interferometric scheme is shown here. If we change a little one distance in this scheme, for example, the distance between this beam split and mirror, then interference picture changes strongly, and it allows to control the distances with very high precision. And in the moment the definition of lens measurement of 1 meter is based on interference. So the meter is defined as um, some number of wavelengths of some sort of radiation. And to obtain this lens, one needs interferometric scheme. And another phenomenon which is related to the interference is appearance of rainbow in such an objects like soap bubble. So like another thin films. So this thin film interference lead to appearance of rainbow colors on the film. It is because of different position of interference maxima for different wavelengths. And that's why different colors produce their maximal intensity interference maxima in different point of our eye. That's why we can see the light decomposed into colors. And another sequence of this interference is diffraction. Diffraction can be defined as a bending of light around the corners of obstacle. And this diffraction limits the ability of optical devices. Especially it limits the ability of microscope. The resolution of microscope is limited by this Abe equation, and this d is the small distance between objects which can be seen as separated objects. There is a diameter of a spot produced by a source, by a point source of light on the image obtained by microscope. So this diameter cannot be zero, and it is defined by this equation. You can see lambda is wavelength, and n is refractive index, sine theta. So theta is angle of converging light going from the object, and this angle theta cannot exceed 90 degrees, of course, and this means that sine theta can get its maximal value of 1. So if we remove sine from here and replace it with 1, we can see that the distance, minimal distance, is equal to lambda divided by 2n. And to decrease d, it means higher resolution, we need to decrease lambda or to increase n. Increasing n is used in so-called immersion objective lenses of microscopes. For the highest magnification factor, the objective lens with a droplet of oil is used. So a droplet of oil is put on a glass, covering glass of the object, and when microscope is used, there is no air between the object and the objective lens. There is a droplet of special oil with some well-defined refractive index. and it allows to increase the resolution. But anyway, we can increase it not so strongly because n is not high for any liquid and for any solid objects. The highest n, I think, is for diamond. It is about 2, and all other materials has smaller n in optical regions. That's why we cannot increase resolution by increasing n, and we cannot decrease lambda because we can see objects only in visual spectral range, only in visual part of this spectral range. And if we use blue light, for example, instead of white light, we can increase resolution, but we will decrease information from colors. We will not see colors if we use only blue light. And there are another way to increase the resolution of microscopes. Well, let us omit the dispersion phenomenon. Let us discuss how we can increase the resolution. One of the ways is to use electron beam instead of light beam. Electrons are particles, and they also demonstrate, they also exhibit their wave phenomena, but the wavelength of electrons depends on their energy and can be done very small. The wavelength of light is a few hundred nanometers. The wavelength for electrons can be done smaller than 1 nanometer and even smaller. So we can get an object that a probe which does not limited by diffraction. But to form an image with this type of probe, we need to enlarge this image. There is no sense if we just make a transmissive image by electrons at the same size of the object. All the microscope devices require magnification, and for this reason we can use so-called electric field lens for electrons. If we put voltages on the cylindrical surface, so here is the picture of a cross-section of electric field lens. Normally this is cylindrical object, and if we apply positive voltage to this part of the device, then the trajectory of electron will look like that, and electron beam which goes parallel initially, then it goes through one point, which is cross-channel point, and this point can be considered as focus, and the device works similar to the optical lens. So this can be used in electron microscope. The electron microscope is the device which allows to obtain highest resolution. Actually, there are some disadvantages, we will discuss it later, but the highest resolution of microscopy which can be obtained is obtained in electron microscopy. So it consists of electron gun, where the hot conductor emits electron, then they are focused, and then they are accelerated by electric field. So this anode is the part of device which accelerates electrons, so the high electric voltage is applied between this electron gun and anode, and it also focuses. Then the beam is focused by a so-called condenser electrostatic lens, and the focused beam goes to the spaceman. After that, the beam should be, the image can be formed, but this image should be enlarged, we need a few objective electron lenses. So this is objective electron lens, intermediate, and projector lens. So there are 3 electric lenses in this scheme of microscope. And finally, electron beam, with which contains information about spacemen, and this information is image of spacemen, but this image is enlarged with 3 lenses. Each finally goes to some sort of sensor. It can be fluorescence screen or some other type of detector. And then the image is formed. If it is a fluorescence screen, we just obtain optical image, because the point which under the action of electron beam becomes light points. But another way to obtain image is to use some electronic scheme which obtains, which measures current. And also this device can be combined with other type of detectors. For example, some detector can measure the energy of electrons, which is called electron energy loss microscopy, and it allows to increase the amount of information obtained from the object. Well, now let us discuss its types and its advantages and disadvantages. So there are several types. It is transmission electron microscope, when the image is formed on the screen. Another way is scanning electron microscopy. In this case, the object is moved. So I see someone has raised a hand. If you have anything to say, please type it in chat. I don't see anything here. So, wait a second. Another way is scanning channel microscopy, when the beam stays on the same place, but the spaceman is moved. That's why the detector also stays in the same place, and the intensity of signal differs with motion of the spaceman, and the image is not formed because every signal goes to the same point, but the image is formed then on the computer by analyzing the intensity combined with the information about the position of spaceman. So the spaceman is moved and intensity is measured. Refraction electron microscopy measures the signal reflected by the spaceman. It is much weaker signal than transmission signal. And scanning transmission is a combination of first and second type of microscopy. And let us discuss advantages and disadvantages. The advantages is, of course, extremely high resolution, because the resolution of electron microscopy is the highest possible. And the second advantage is possibility to combine another technique with the microscopy, such as measurement of electron energy. But there are some strong disadvantages. It is the basic disadvantage is strong requirement for samples. The samples should be very thin. They should be transparent for electrons. They should contain some substances which absorb electrons strongly, so we need to wait a second, to use some sort of substances to prepare the samples. and that leads to very complicated procedure of sample preparation. And we cannot watch living objects in electron microscope because the sample preparation includes a lot of phases which will kill any living cells. So only if we want to have very low resolution, we can see the living object, but in most cases we cannot see anything. And the last disadvantage of electron microscopy is high cost of these devices, because it includes a lot of very highly technological things. It requires very high vacuum inside. It requires very precise location of electron lenses. So many difficult to create things are used in electron microscope. That's why it is a very expensive device. And there are some alternatives for this. One of alternatives I'd like to discuss is scanning probe microscopy, which is much simpler. It is one of them is atomic force microscopy, where the force between a small needle and object is measured. It is measured by inclination of so-called cantilever tip, and the inclination is measured using laser beam and detector. So this microscope allows to obtain the same strongest resolution, atomic size resolution. It is the same as an electron microscopy. Sometimes, actually, electron microscopy sometimes gives higher resolution, but atomic force microscopy has the advantage that it does not require such a complicated procedure of sample preparation. The samples can be made much simpler here. Another way of scanning probe microscopy is scanning channeling microscopy, which is applied for conductive objects when not a force but electric current is measured between the probe and the spaceman. There is another way, so-called near-field optical microscopy, when the light is the light goes to the needle, to the tip of the needle, and the interference picture is then analyzed. In this case, we can get the picture with resolution smaller than wavelengths, and due to interference. And one more way to increase resolution is so-called confocal microscopy, when the light source and light detector uses the same optical system, the same objective lens. So light is not going from the bottom of the object as in normal microscopy, but it goes through the same objective lens system. And when light goes back, it comes through the small aperture diaphragm, and that's why the dip of the sharp vision is becomes very low, and it allows to see the objects which are located at some focal plane without signal from the planes below it, and which is closer and farther than the focal plane. This technique allows to obtain the pictures the three-dimensional model of the object, because it allows to get signal not only in focal plane but in the direction perpendicular to the focal plane. And this device uses scanning technique, because the signal is obtained from one point only at the same time. That means we don't have an image, we just have an image of one point, and we can measure its intensity. If we move spacemen in this scheme, we will get signals from different points, and then analyzing this signal with a computer, we can get an image of object. This technique actually does not allow to increase the resolution strongly. It increases resolution because the monochromatic light is used. The source of light for this is usually a laser. It is a source of monochromatic light, but in addition to increase of resolution, it allows to increase contrast of the object. That's why images created by this technique is looks much more informative than images created by normal microscopy. And another way to increase information obtained by microscopy of this type is to use the fluorescence. If we put some substances inside the object, then we can get information from only those points which include this substance, this fluorescence ink and fluorescent dye. And if we then so fluorescence is the light with different wavelengths than the light of the source. And if we remove the signal at the same wavelength which was used as the source and obtain only the signal at wavelengths of fluorescence, we can get very constant pictures of very small objects. So these techniques are widely used in biological and medical studies. Now let us stop at this moment. So let me see the questions for your final test. I can see it here, final test. And you see that